Hi, in this video we are going to go through some worked examples looking at null spaces of matrices, special solutions to homogeneous systems, general solutions to non-homogeneous systems, and rank. Let's begin with some problems trying to find the special solutions to a homogeneous system and to describe the null space of the corresponding coefficient matrix. We're going to look at three different systems. You can either pause your video now and go through and try to work through all three systems, and then resume, or you can continue and pause before we consider each individual system. So let's begin with the first. A 3 by 3 coefficient matrix, and we find the special solutions to this homogeneous system of AX equals 0 and describe its null space. Pause your video and then resume after you've completed your own work. The first step in this kind of problem is always to find the reduced row echelon form of the coefficient matrix. We do this with Gaussian elimination, which by now ought to be familiar and smooth. We start with the first pivot, eliminate downwards. This gives us 2 minus 2 is 0, 4 minus 4 is 0, and 3 minus 2 is 1. And 1 minus 1 is 0, 2 minus 2 is 0, 4 minus 1 should be 3, not 2. Then we move over and to the right. We would use this entry for a pivot. It's 0 and already has zeros below, so we simply skip, move over to our next pivot, and eliminate downwards. 3 minus 3 gives us 0. Right? This is now a echelon form, but not a reduced row echelon form. We eliminate upwards, starting with our pivot here, and eliminating this entry to give us 0. And now we are in a reduced row echelon form with 1s in the pivot positions and all 0s everywhere else in the pivot columns. Now let's take a look at this. We have two pivots, one free variable. x2 is a free variable. The number of free variables equals the number of special solutions. One free variable, we need to find one special solution. How do we find that? Well, we start by setting up a vector that has the single free variable of x2 set to be 1, and the remaining positions unknown. These are the pivots of x1 and x3. And then we go to our original matrix and find that free variable column and select the values to fill in for the pivots from this. The pivot in x1 has a 2, so that becomes a -2 in the special solution. The row containing pivot x3 has a 0, and so that becomes a 0 in our special solution. This vector -2, 1, 0 is the one special solution. Once we have the special solution, we can describe the null space. The null space is the set of all possible linear combinations of this special solution. That is, it's the set of all vectors where x can be written as some number, any real number, multiplied by xn. The set of all multiples of a single vector, of course, is a line. So in this case, the null space is a line. Okay, now let's consider another case. in this case, a 4 by 3 coefficient matrix. I recommend you pause your video, work through the solution if you haven't already done so, and then continue on. Once again, we begin by finding the reduced row echelon form of this coefficient matrix. Start at the upper left, use this as a pivot to eliminate downwards. 2 minus 1 is 0. 2 minus 2 is 0. 3 minus 4 is negative 1. 3 minus, apologies, there is a error here. 3 minus 2 should be plus 1. Sorry for that. 1 minus 1 is 0. 0 minus 2 is negative 2. 2 minus 1 is 1. 2 minus 2 is 0. 2 minus 4 is negative 2. 1 minus 2 is negative 1. Again, this should be a plus 1 here. We then continue forward, moving over and down to our next pivot. Eliminate downwards. Negative 1 is a negative 2 plus 2 is 0. 2 plus, and I'm going to have to correct this, 1 plus 2 is, this will be 1 minus 2, so this should be a negative 1. We'll put a negative 1 in here. Negative 2 plus 2 is 0. Negative 1 plus minus 2 should be negative 3. Negative 3 here. And then we would move over and to our next pivot, and once again eliminate downwards. It does give this row. These mistakes actually don't propagate through to our answer because in our next step, now that we have our row echelon form, our echelon form, but not our reduced row echelon form, we eliminate upwards with this value, going to eliminating up this column to give all zeros, and then move over and to the left, eliminate upwards and scale to a positive 1, giving us our final reduced row echelon form. The final form we get here has pivot, 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 3 pivots, each in a column of all zeros, and no free variables. When we have no free variables, that means the only solution to bx equals 0 is the 0 vector. The null space is just the 0 vector, the origin. There are no special solutions because there are no free variables. Okay, let's consider one more example. Find the special solutions to this homogeneous system, in this case a 3 by 4 matrix. If you haven't done so yet, I recommend you pause your video, solve this system, and then resume. Once again, we start with our finding our reduced row echelon form, use our upper left pivot to eliminate downwards. 2 minus 2 is 0, 4 minus 4 is 0, 2 minus 2 is 0, and 4 minus 4 is 0. The second row is a scalar multiple of the first, so it becomes a row of all zeros. 1 minus 1 is 0, 2 minus 2 is 0, 3 minus 1 is 2, and 0 minus 2 is negative 2 for our third row. We have a row swap needed here, so we exchange rows and then move over to our next pivot. We actually recognize at this point we've already eliminated downwards. We are in our echelon form. We now move to our reduced row echelon form, scale this row to a 1 and a -1, and eliminate upwards, subtracting 1 minus 1 is 0, and 2 minus -1 is 3, to give us our reduced row echelon form. 2 pivots that are 1s with all 0s everywhere else in the column. How do we analyze this system? 2 pivots. We, in this case, have 2 free variables. Both x2 and x4 are free variables. We will need to have 2 special solutions. How do we find them? We initialize our vector. They are represented, they're 4 vectors from 4 space. They have 4 variables because we had 4 columns in our original vector. We set one of the free variables, x2 equal to 1, and the other to 0. And then we have to ask what are our pivot entries for that vector. Since x2 is the one we set to 1, we look at the x2 column, and our pivot entries will be here. For x1, we have a 2. We negate that in our special solution. And for x3, we have a 0, so we have a 0. Our first special solution is -2, 1, 0, 0. For our second special solution, we again take a look at our 2 free variables. We set the other one to 1, and in this case x4, and then x2 to 0. And then once again, take a look at the x4 column to fill in the pivots. The x1 row has a 3, so we negate that and put it a -3. The x3 position has a -1, so we negate that and make that a +1. -3, 0, 1, 1 is our second special solution. Once we have our special solutions, we can characterize the null space. The null space is the set of all possible linear combinations of these 2 vectors. It is s times xn1 plus t times xn2 for any s or t in R. When we have two special solutions, the null space is a linear combination of a set of all linear combinations of 2 vectors, which is a plane. All right. We've now gone through 3 examples of finding special solutions to a homogeneous system. I'd now like to work through 2 examples finding the general solution for a non-homogeneous system using the form that we've discussed in the videos of a particular solution, single particular solution, plus a set of linear combinations of special solutions. Let's begin with this linear system. I recommend you pause your video, try to find the general solution in this form, and then continue to watch the worked solution. When we're looking at a general solution, we again begin with the reduced row echelon form, but we look at the reduced row echelon form of the augmented matrix, not of the coefficient matrix alone. The reason for this is that by working with the augmented matrix, we will be able to pull out the particular solution as well as the special solutions. So again, Gaussian elimination. Eliminate downwards. 2 minus 2 is 0, 2 minus 2 is 0, 1 minus 4 is negative 3, 1 minus 4 is negative 3, and 2 minus 0 is 2. 3 minus 3 is 0, 3 minus 3 is 0, 3 minus 6 is negative 3, 3 minus 6 is negative 3, 2 minus 0 is 2. 1 minus 1 is 0, 1 minus 1 is 0, negative 1 minus 2 is negative 3, another negative 1 minus 2, negative 3, and 2 minus 2 is 0. We notice now we move down to and notice we have 3 identical rows. We're going to get 0 rows in the next step. Just to be clear of how that happens, we move down and over to our next pivot, but it's a 0 in which already has all zeros below, which means we can just move right over to our next pivot and eliminate downwards. Because all of the rows are identical, this elimination step is going to create all zeros here. We have an echelon form with 2 pivots, but we carry it all the way through to a reduced echelon form. Divide this second row by negative 3 to give us a 1 in the pivot position, and then eliminate upwards. 2 minus 2 is 0, 2 minus 2 is 0, and 0 minus negative 4 over 3 is 4 over 3. This is now our reduced row echelon form. 2 pivots that are 1s in columns of otherwise 0. And remember that this last column is our right-hand side column, whereas the first block corresponded to our coefficient matrix. Once we have our augmented matrix, we're ready to pull out the special solutions and particular solutions. They are all directly encoded in this matrix. We just have to read it in the right way. We don't have to do any more work, any more calculations. Recall that we have pivot, 2 pivots, x1 and x3, and 2 free variables, x2 and x4. The last column is our right-hand side. It is not a free variable. Okay. How do we then generate our special solutions and our particular solutions? Special solutions are generated in exactly the same way. 2 free variables, x2 and x4. First of all, set x2 to be 0 and x2 to be 1 and x4 to be 0. We're looking at x2, and so the pivot variables are in that column. For pivot x1, we have a 1. That becomes a negative 1 in the vector. And for pivot x3, we have a 0, so we get a 0 in that position. First null space vector, special solution. Second special solution, we again look at our free variables. We set now x2 to be 0 and x4 to be 1. That means we're looking in the x4 column. This is where we're going to pull out our values for the pivot variables. The value for x1 is 0, and so we put in a 0. The value in the x3 pivot row is a 1, so that becomes a negative 1. And this gives us our second special solution. 2 free variables, 2 special solutions. We have those. Now we additionally need to write down our particular solution. Our particular solution is hiding in this last column. Again, we first of all identify our free variables. And for our particular solution, we set them both equal to 0. After doing that, our pivot variables are hiding in the last column. Not really hiding in plain sight, if you will. The x1 position is a 4 over 3, and the x3 position is negative 2 over 3. The only tricky piece here is to note that for the null space, we negate the entries in the free variable columns. And for the particular solution, we don't. This really comes from the fact that in the coefficient matrix, the free variables are on the same side as the pivots. And to move them over to a solution, we have to move them to the other side, which is where we get negation. And for the right-hand side, we don't have that process, so we just take the numbers as they are. Now that we've identified our two special solutions and our particular solution, we can write down our general solution. The general solution is our particular solution that we just found, plus any possible linear combination of our two special solutions. We can leave it in this form where we have just an algebraic form with the particular solution and the special solutions defined as vectors, or we could substitute in xp, xn1, and xn2 and evaluate this to get something that looks more like the parametric solution that we've seen in from previous approaches. Either of these is a valid way to write the general solution. Okay, let's take one more example. The following solution, the following system. I recommend you pause your video, try to find the general solution, again in this general form. When you've done so, carry on and follow through my work solution. Once again, we start by trying to find the reduced row echelon form of the augmented matrix because we're trying to find a general solution. This is a 3 by 5 coefficient matrix, so we have 5 unknowns, 3 equations. It means our coefficient matrix is going to have our augmented matrix is going to have 6 columns. And we carry on Gaussian elimination in the usual way. This matrix actually looks a little bit interesting. When we start off, we have a 0. This happens, but what is less common is that we have a 0 in this upper corner, but we also have zeros all the way down. There's nothing to do for elimination. We just move over to the next pivot, or to the next column for a pivot. This is our pivot variable. We eliminate downwards, nothing to be done for the second row, but we subtract the first row from the third. 1 minus 1 is 0, 3 minus 2 is 1, 4 minus 3 is 1, 2 minus 2 is 0, and 1 minus 2 is negative 1. That gives us our third row. We now move over and down to our next pivot and eliminate downward. Because the third row is now identical to the fourth, or to the second, this gives us a row of all zeros. We are now in an echelon form with 2 pivots, but not in a reduced echelon form. The reduced row echelon form we get by eliminating upwards from our bottom pivot. 2 minus 2 is 0, 3 minus 2 is 1, 0 minus 4 is negative 4, and 2 minus negative 2 is plus 4. This is now our reduced row echelon form, 2 pivots that sit as isolated values of 1 in columns that are otherwise 0. Now that we have our reduced row echelon form, we are ready to pull out our special solutions and particular solutions. 2 pivots, x2 and x3, and 3 free variables. Any column that does not have a pivot in the coefficient block is a free variable. Sorry, that one is not a free variable. x1, x4, and x5. This should say x4, x5 are our free variables. x2 and x3 are pivots. Remember that this last column is our right-hand side. It does not correspond to a free variable. 3 free variables mean we will have 3 special solutions, but we generate them in the same way. We identify our 3 free variables, x1, x4, x5. And we then set our first one to 0, x1 equals 0, and the others to, first one to 1, x1 equals 1, and the others to 0. To get the pivot entries, we look in the column corresponding to that first free variable, x1. That's this position here. And we have zeros in the position that corresponds both to x2 and to x3. So we get 0 and 0. For our next special solution, we set x1 equal to 0, x4 equals to 1, and x5 equals to 0. These again are our 3 free variables. And to find the values for the pivot entries, we look at the 4th column and read out those numbers. For x2, there's a 1, and for x3, there is also a 1. Negate these in the answer, so we get a -1 and a -1. This is our second special solution. Our third special solution comes from, again, looking at our 3 free variables. x1 and x4 are 0 in this case, and x5 is 1. The pivot variable entries come from the x5 column. We have a -4 corresponding to x2, so that becomes a +4 in the vector, and a 2 corresponding to the x3, so that becomes a -2 in our vector. 3 free variables, 3 special solutions read off of this matrix. Before we put it all together, we also need to find our particular solution. This is found by, again, starting with our 3 free variables, but setting all of them equal to 0. And then looking in the last column, the right-hand side column, to get the pivot areas without negation. For x2, it's a 4. For x3, it's a -1. So we get these. Now that we have 3 special solutions and our particular solution, we can put it all together. The general solution is simply our one particular solution plus a coefficient multiplied by our first particular solution, a different coefficient multiplied by our second, plus a different coefficient multiplied by our third, where these coefficients can take on any values. The set of all linear combinations of our special solutions plus our one particular solution. We can leave it in this form with our defined vectors, or we can put this in something that looks more like the parametric solutions we've seen before by substituting in xp, xn1, xn2, xn3, and simplifying the result. Okay. We've now gone through a few examples of finding special solutions for a homogeneous system, finding general solutions to a non-homogeneous system. I want to wrap up this example with a few examples of actually a much simpler problem, finding the rank of a matrix. So let's start with these 3 matrices. Please pause your video, compute the rank of each of these, and when you think you have your answer, move forward to compare with my solutions. All right. To find the rank, all we need to do is to reduce to echelon form. We do not have to take things all the way to reduced row echelon form. And then we simply count the pivots. For matrix A, start with our upper left pivot, eliminate downwards. 2 minus 2 is 0. 1 minus, negative, this should actually be 1 minus 4, so this should be negative 3. And 3 minus, I'm really not sure what happened with this one here. 3 minus 6 is negative 3. We have 2 pivots. 1, 2. In an echelon form, the rank is 2. For our second matrix, do the same thing. Start with our upper left pivot, eliminate downwards. 2 minus 2 is 1. 1 minus 4 is negative 3. 2 minus 2 is 0. 1 minus 1 is 0. Negative 1 minus 2 is negative 3. 1 minus 1 is 0. Then we move over to our next pivot, eliminate downwards. The rows are identical, so this gives us a 0 row. We now are in our echelon form, 1 pivot, 2 pivots. 2 pivots, the rank of this matrix is also 2. For matrix C, do the same thing. Start in the upper left, eliminate downwards. Nothing to do for the second row or the fourth row. But for the third, we subtract the first. 1 minus 1 is 0. Negative 1 minus 1 is negative 2. 1 minus 1 is 0. We then move over and to the right. Eliminate down again. Negative 2 plus 2 is 0. 0 plus 4 is 4. 2 minus 2 is 0, and 4 minus 4 is 0. We now have an echelon form with 3 pivots, and so the rank of this matrix is 3. Very straightforward, simply reduce to echelon form. We do not have to go all the way to reduced echelon form, and count the pivots. I want to wrap up with one more very quick example. Find in special cases where matrices have simplified forms, we can find the rank without even needing to do elimination. And so I want to just give a little bit of practice here. Consider these 3 matrices and identify their rank without going through elimination. If you want to take a few minutes to think about it, pause and think, and then carry forward. All right. Matrix D has already 2 0 rows, and the non-zero rows are identical. This means that if we were to take even a single step of elimination, we would get to all 0 rows except for 1. This tells us that the rank of this matrix must be 1, a rank 1 matrix. Any matrix where all of the rows are scalar multiples of each other is a rank 1 matrix. Matrix E is the 0 matrix. All rows are 0. There are no pivots. If there are no pivots, the rank is 0. This is a special case. The only matrix that has rank 0 is the 0 matrix. Finally, F is an identity matrix, 4 by 4 identity matrix. That means it's already in reduced row echelon form. We simply count the pivots, 1, 2, 3, 4, and we have a rank of 4. All right, that wraps up these worked examples for Unit 6. Thank you and goodbye.